Hi, I'm Zor. Welcome to Unizor Education. We continue talking about parabola. In the previous lecture, I basically gave you the definition of parabola and derived equation of parabola in Cartesian and polar coordinates. Today we will talk about parabolas optics. We did actually go through optics for ellipse and for hyperbola. So if you remember, in case of ellipse, we had two foci, and if light is emitted from one foci in any direction, it will always go to another one. In case of hyperbola, if you go from one foci with a ray of light, it actually will be reflected this way. But if you will continue the line, it will cross another focus. So in both cases, the line of reflection goes through another focus. In case of parabola, the situation with optics is slightly different because we have only one focus. So in case of parabola, you have something like this. This is focus. So my point is that the light emitted from the focus will be reflected parallel to the main axis of symmetry. So all the rays will go parallel. So that's actually the reason why if you have some kind of a mirror which is supposed to reflect the light far away, the mirror is always parabolic. Okay, so we will talk about this, but right now let me just tell you that this particular lecture is part of the course. The course is called Math Plus for All. It's presented on a website called unizor.com. If you found this lecture somewhere else, like on YouTube for example, well, you will find this lecture just by itself. But if you will go to the website, it has a menu. It has all the courses as the top menu. Within the course you have certain subjects. Let's say Math for Teens, the prerequisite course for teenagers. It contains subjects like algebra, geometry, trigonometry, etc., etc. Math Plus also contains some of these topics. This is just in addition to whatever the Math for Teens is. And within the particular subject of particular course, let's say this is Math Plus course, but the subject is geometry, and within geometry you can find lower level items, like in this particular case, this lecture will be under geometry. In some cases, my menu is has even more layers. Within the subject, I have a group of lectures, and then within the group, I have something like subgroup, etc. So anyway, using the menu, you will get the complete picture of the course, and it's presented in a logical sequence, obviously. So if you will go top to bottom, you will always be using certain information which you have learned before in the next lectures. They are very much related one directionally, so to speak. Now, there are also courses like Physics for Teens, Physics Plus for All, not completed yet actually. There is a course called Relativity for All. So that's an interesting thought. So now everything is totally free. You don't have to sign in or anything like that if you don't want to, unless you are studying under somebody's supervision. So if you have a supervisor like a teacher or a parent, then you must actually establish the connection, and then you need to sign in. But that's just basically name and password. Okay. Let's get to parabola. So as I was explaining, this is the property of the parabola which I would like to prove today. Okay, so let's do it more mathematically and less physically. So mathematically, I did mention it before when I was talking about optical properties of ellipse and hyperbola, but I'll mention it again since it's kind of an independent lecture. What is reflection of the curve? Whenever we're talking about the reflection from this ellipse or hyperbola, we were reflecting of the curve. We all know that the reflection of the straight line is basically something like this. If this is the ray of light, now this is called incidence and angle of incidence. This is reflection, and these angles are equal. That's the law of reflection. But obviously these two also are equal because they are complementing to 90 degree. So this is the law of reflection for the line. Now how about the curve? Well, for the curve, situation is very much similar. If you have a curve and the law of reflection of the curve is the same as law of reflection of tangential line at the point of reflection. So basically, again, all you need to do is to draw a tangential line at the point where the light actually goes, and then do whatever is necessary according to the laws of reflection from the line, which means angles of incidence and reflection are the same. Okay. Now, so I will use this in case of our parabola. So let's just do it. Okay, for example, this is xy. Now somewhere there is a directress at the distance c from this vertex of parabola. This is vertex 0, and this is the focus also with the c. So if you remember, parabola is a locus of points equidistant from the focus and from the directress. So obviously the midpoint between the directress and the focus, which is would be such a point on the parabola, and then it goes this way and this way. So the difference, there is no difference between distance this and this. Okay, so let's say this is point P, x, y, and I would like to prove that the reflection would be parallel to the axis of symmetry of parabola. So that's what I want to prove. Okay, again, to basically to talk about the reflection, I have to have a tangential line. So let's say this is tangential line. Let's say A, B, and this is S. So from the reflection law, I know that this angle from the incident ray to tangential line should be equal to this. So that's basically from the law of reflection. So this is, well, if you put a perpendicular, so this angle is 90 degree minus incident angle, and this is 90 degree minus reflection angle, because reflection and incident are from the normal perpendicular line to a mirror. Well, but doesn't really matter. But if I will prove that, I mean, I have to use that these two angles are the same based on the laws of reflection. Now, how can I prove that this line is parallel to this line? Well, remember, when you have two lines and one intersection, if these angles are equal to each other, this one and this one, then two lines are parallel. So this is one of the first theorems about parallel lines, which obviously are covered in the previous course, prerequisite course called Math for Teens. So I will use it, and to prove the parallelism of these lines, regardless of there is the point P, I will have to prove that this angle is equal to this angle. Let's call it alpha, and this is angle also alpha because of the reflection law. And this is angle, let's say, phi, and this is angle psi. So I have to prove that angle psi is equal to angle alpha. That's what I have to prove. From this would follow the parallelism. Okay. Now, what I will use is the two things. Well, first of all, that this alpha is equal to this alpha, and also I will use the fact that this is a parabola. What does it mean that this is a parabola? Well, we have derived the equation of parabola in a previous lecture. So we'll use this. So x and y satisfy this particular equation. All right. Now, instead of proving the angles are equal, I will prove their tangents are equal, because, you know, the tangent is so this is pi over 2, this is pi, this is minus pi over 2. So tangent just goes this way. Oops, too much. Sorry. Pi over 2. So from 0 to pi, and all the angles are from 0 to pi, the tangent function is monotonic. Well, except it's not really defined at p over 2, but we can consider this case separately, and quite frankly, I don't want to spend too much time on these details. I'll just do it in a general case. So we are assuming that this angle is not actually pi over 2, because then it will just reflect. You see, okay, fine, I'll spend some time. If you will put perpendicularly to this particular line, it will basically reflect to itself. So it's basically the only thing which we need. Okay. Now, and there is only one actually point where the perpendicular is to a tangential line is possible. If tangential line is y-axis, then the ray would be perpendicular and it will go again parallel to x. So that's a separate case, but we don't have to consider it, although we are already considered. All right, so I will use the equality of the tangents of these two angles, alpha and psi. All right. I will approach it the following way. First of all, I would like to make a relationship between alpha, this alpha, it's equal to that one, and phi and psi. Well, you know that the sum of the angles of triangle APF is equal to 180 degree pi. So angle psi plus angle alpha plus angle which is pi minus phi equals to pi, from which follows that well, pi will cancel, alpha would be equal to phi goes this way, and this was a minus to the psi. Okay, so this is the relationship. So how can I find the tangent of alpha? Well, obviously there is a formula for tangents. Tangents of, let's say, a minus b is equal to tangent a minus tangent b divided by 1 plus tangent a tangent b. So this is a formula from trigonometry, and again it's part of the course Math 14s, so I'll just use it. Tangent of difference between angles is difference of tangents divided by 1 plus product of tangents. Okay, so to get the tangent of alpha, I have to know tangent phi and tangent psi. Okay, fine. Now, tangent phi, well, that's easy. If you will put perpendicular, it will be length of this divided by length of this. Now, length of this is ordinate of this point, which is y, and this is equal to ordinate minus abscissa minus x. So it will be x minus c, not s, sorry. Okay, and this is what? This is my tangent phi. How about psi? And I will use exactly the same as before when I was talking about optics of ellipse and hyperbola. Well, this is a tangential line to parabola, and I know that tangential line has a tangent with the x-axis, which is tangent of psi, is equal to first derivative of the function at the point at x. Again, that's part of the calculus course, which is part of the maths for teens. Okay, this is elementary calculus, and now we have to find this, but we have this. This is the equation of parabola. So how can I get this? Well, very easily. Let's just differentiate both parts. The derivative of y squared would be 2y times derivative of inner function, which is derivative which I would like to find out. Derivative of this, now 4c is a constant, so it's 4c, that's a derivative, from which y is equal, the first derivative is equal to 4c divided by 2y, which is 2c divided by y. Let's remember this. So from this, from the equation of parabola, follows this equation of equation for its derivative. All right, fine. So let's just have it here. That 2c divided by y is tangent psi. Great. Now we will use this function, this trigonometric equality, identity actually, trigonometric identity, to find tangent alpha. So it's difference between these tangents, which is y over x minus c minus 2c over y, divided by 1 plus their product, y x minus c y 2c, right? Okay. Okay. Now, okay, let's just simplify this thing, because all we need right now is to simplify. If you will get to the common denominator would be y times x minus c. Common denominator of this also y times x minus c. So I can actually get these both to common denominator and ignore the numerator of each of them, right? So that would be equal to y squared minus 2c times x minus c, minus 2c times x minus c. Now here would be y times x minus c plus 2cy. Okay. Now this is equal to Now, instead of y square, I can always put that, right? Because we are talking about parabola, it's all points on the parabola. So it's 4cx minus, open the parenthesis, minus 2cx and plus 2c squared. And at the bottom, I will have xy minus cy and plus 2cy. So it will be plus cy. Alright? Okay, now 4c minus 2cx, that will be plus 2cx, which is equal to uh, 2c times x plus c, and here we have y times xyc. So xyc and xyc would cancel out, and this is my final result. Now look at this. Tangent alpha is equal to c over y, but tangent size also is equal to c over y, which means tangents are the same, which means angles are the same. So psi and alpha are the same. And since this alpha and this alpha are the same, so this psi is equal to this alpha, which means these two lines are parallel. And that's independently of x and y. So parallelism is independent on the point wherever ray of light actually goes. It will be here, it will be here. If you put here, it will be here. It's all parallel to x-axis, to axis of symmetry. Well, basically that's it. Now again, let me just say it again, that in some places where we need to actually direct the light to one direction, we are using parabolic reflectors, mirrors, if you wish. Okay, that's it for my presentation. So what I suggest you to do is, every lecture on the Unizor.com has written notes, which basically is like a textbook. I was trying not to miss any kind of a detail in this writing, so I suggest you to read whatever is notes for this particular lecture. And that's about it. So thank you very much and good luck.